All right, and we're in our last section of sensation and perception. We're on to the part of perception, and this is all going to happen, excuse me, in our brain, of how our brain is going to perceive all these neural signals that our senses just sent over. Okay, and we're going to start with the first little section, which is perceptual set. And this is basically a set of mental tendencies and assumptions that is going to affect the way that we perceive the world. Okay. This is what affects how we hear, we taste, we feel, and see. Okay. And this is basically where we form our concepts slash schemas that help us organize and allow us to interpret unfamiliar information. Okay, so perceptual sets, it's kind of like your schemas that as we're experiencing, it's going to put things kind of like in a like patterns and organization in order for us to like pick up information a lot faster as we're experiencing life. Okay, so that's perceptual set. Now, they've done this like an example, a little study is let's say they put like French fries in a McDonald's bag, but there was not McDonald's fries in there. And so what they ended up doing was like, since it was from a McDonald's bag, they'd be like, okay, which one is like your favorite fry? And people would pick McDonald's fries, even though it wasn't. But they believe their schema was, well, McDonald's fries are better than, let's say, Burger King. Okay. So there's that. Wherever you stand on that, wherever you stand. All right. Then you have what's called context effects. Okay. And this is where the context of the situation is going to affect the way that you perceive the situation. So, for example, if you were hearing somebody say, like, right before, like, oh, she's really pretty, and then somebody says something that sounds similar, you're gonna believe that, oh, they were talking about something that's pretty. Or if you were listening to a song, right, prior, and then you hear a song that sounds like it, you're gonna think, oh, it was a song that I just heard. Okay, so it's kind of like we make our perception based on our experience or in the context of where we're at. Okay, then we have emotions and perception, and how our emotions are going to affect the way we perceive things. And that's exactly what that means. Okay, so we are in, like, our emotions are going to influence the way that we perceive something. So like, let's say we're having like a really bad day and somebody says something to you, you may perceive that as they were being mean to you or annoying, even though they might have been just neutral, right? This is why when you're like not having a great day and somebody says something to you, you're like, oh my gosh, why did they say it like that, or whatever. So, and if that has happened to you, I get it. Okay, but this is a cool one to get because it really does affect the way we interact with people or the perception of what happens to us, our experiences. There's a cultural effect, which our culture can affect the way that we perceive certain things. And they've done studies that different cultures can actually see the same stimulus and respond to it in a different light. Okay, and it's basically our culture is going to determine what we're paying attention to, what's important to notice, what's funny or offensive. Okay, and this is also what's going to shape our stereotypes. Right, make sure you have all of that. And then there's what they call extrasensory perception, which is ESP. And this is where a person can read another person's like mind or perceived future events in the absence of concrete sensory input. Now, there's no evidence of ESP. An example of this can be like, let's say you're thinking about somebody and you're like, oh, I know they're gonna call me, or I'm gonna see them, and then poof, all of a sudden you see them, or they call you. Okay, that could be that, or knowing like something's gonna happen and you could see it, and then boom, it happens. Okay, but again, there's no what's this called? There's no evidence for this. All right. So we're going to go on to the next little section of this, which is visual organization. Okay. And I gave you some visuals here. So if you could draw it out and add it, because this will definitely help you understand what these concepts mean. Okay. And this is basically how our brains are going to organize information that comes through our senses. Okay. And we're going to start with the first one, which is Gestalt principles. And Gestalt principles is basically that we're going to look at things as a whole. We're going to put it together. They say that our brain will put together the information and as a whole, and then boom, that's how we're able to see a whole picture. Okay. Now, they really focus on getting like the little pieces of things that pieces are gonna come together to make a whole. All right, so make sure you have that. Now, one of the principles of Gestalt, it's called figure ground. And by the way, College Board loves to have this in there. Figure ground is basically where we organize the organization of our visual field into the object, which is the figure, that will stand out from its surroundings, which is the ground. So if I look at this vase here, I'm gonna zoom in here so you could see, or this vase or faces. If I'm looking at the white part, which is the vase, that would be the figure. The black part would be the ground, okay? But now I could shift my vision, right? And now if I look at the black part, which is the faces, that would be then my figure, and then the white part would be the ground. Okay, so we can, that's, luckily for like that parallel processing allows us to kind of like switch over and do that. But in actuality, we're not able to see both like the vase and the face at the same time. We're seeing them actually separate. Okay, just like this one, right? If you're looking at the black part, right? Or if you see a face, that's going to be the figure, right? I'm looking over here. And then the black part is gonna be the ground. Because if you see the girl's face, that's the figure, and the black part is the ground. Now, if you could see just the black part, it's a guy playing a saxophone, and then the lady's face is then the ground, okay? Now, they also talk about grouping, and basically they said that our brain is all about grouping and finding patterns. And this is where we're going to be able to organize this information into meaningful forms. And we do this by a couple things with grouping. And the first one is proximity. So we basically group, okay, which is right here. We're gonna group things together, figures together, if they are near each other, okay? This happens sometimes, like if you ever gone into a restaurant and you go in with your family and like another family comes in and they think that since you're close by, you must be all together. Okay, that's a little example of proximity. Then there's also what's called continuity. And continuity is basically that we perceive smooth and continuous patterns rather than discontinuous ones. So when we look here, something like this, we don't see this as broken up lines, right? We see them as one long line and this all together, when in actuality, it just can be in parts, but we see it as a continuous. We don't see it in parts, okay? Then there's closure. And closure is that when we see, we basically fill in gaps to create a complete whole object, okay? So even if we don't see this, let's say, as a circle, because it's really not a circle, we still see it as a circle, okay? And then here, we could create a triangle, even though there's really no triangle there. So our brains are meant to create these closures. So it's pretty cool how it does that. And then we also have what's called similarities, and that's when we tend to group similar objects together in our perceptions. Okay, so this is either a row or a column, so depending on how you're going to put it as similarities. It could be in pattern similarities or just all X's and O's. All right, so that we have it for Gestalt principles. Please make sure that you know this is how we kind of see things as a whole, like from pieces to whole, using these principles here, okay? Now we're gonna go into depth perception. And depth perception is basically knowing the depth of something, right? How we're able to see basically 3D, three-dimensional. Okay, and they figured that the way that they did this is they started what's called the visual cliff. And the visual cliff was a lab experiment that they did with infants that were from 6 to 14 months. Make sure we're writing this down. And they put them over this kind of glass thing that looked like there was no glass, right? Like if it was going down. And they were basically testing the depth perception of infants and when they developed that. And so basically when the baby wouldn't cross over through the glass is when they had already learned depth perception. So they say about after I think it's around 8 or 9 months that they start developing this depth perception, sometimes earlier. Okay, so thanks to our two eyes, right, we have what's called binocular cues. Bi meaning two, so two eyes. Our two eyes are basically what allows us to see, but since they are where they are in our face, we actually see different, like both eyes are seeing things differently. And as you see here, okay, in this image, they're seeing things differently, the left and the right eye, and then it basically puts it together to see that one image, okay? And there is what's called retinal disparity. And please know this word, I don't know why College Board loves to use it. Retinal disparity is where we're able to, using both our eyes, perceive depth, okay? And so what retinal disparity does is it compares the images from the retina in the two eyes, and then the brain computes the distance between those two images that the eye sees, both eyes see, and then if the greater the disparity between the images, the closer the object is, okay? And the way that it does that is what's called convergence. Now, convergence, make sure to write that down, is how far inward your eye needs to move when focusing on an object. So the closer something is to your face, the more your eyes are gonna go inward to like looking at your nose. So if you put your finger, your index finger, all the way to the front, and you start moving it closer to your face, your eyes will start moving inward, which is convergence. And convergence is just, it allows us to know how close something is by the eyes moving inward, okay? And then retinal disparity, a great way to know this, and I mean, I don't know, I used to do this when I was in school. How my teachers let me get away with this, I have no idea. But I would put a pencil, I would get bored, and I would put a pencil in front of my, right in front of me, and then I would open like one eye and the other eye, like only have one eye, and just to see the pencil moving from side to side. Okay, I was bored, but don't judge. But anyway, but that is retinal disparity, right? It's technically your eyes, one eye is gonna see the item differently than the other, but with both eyes open, your brain puts it as one, okay? So that allows us to see some depth. Now, we're gonna move on to what's called monocular cues. And I will say there's a lot of them. College Board loves to use these, okay? So definitely finding little strategies, drawing things will be very helpful for you to remember this. So monocular cue is how we're able to see depth, right, with only one eye. And if you like taking pictures or photography, they're gonna use monocular cues sometimes to create like an illusion within those images, okay? Because your like a camera only has one lens. So they're using monocular cues. All right. So there's different types. So the first one is going to be interposition. And interposition is basically if one object is blocking another's view, we believe that the one in the front is going to be closer, okay? When in actuality, they're two flat, two-dimensional things. Like if you see here, this one looks like it's in the front, and while this one's in the back, when in actuality, they're literally side by side. Okay, so that's interposition, right? Like here we see this image too. I have a few images so you could get an idea. And if we look at these two things, technically they're side by side, but we will see the blue as being in front because it's in the front position, right? It's blocking the one in the back or the red. Okay. Then we have what's called relative size. Okay. And relative size is which we perceive something as further away because it looks smaller than the object in the foreground. Okay. So we will assume, like, if you look at these two things, this one looks like it is further away than the one that looks bigger. Okay. And that's just a way that our brains kind of process this information. Pretty, it's a little trippy. Okay, the next one is gonna be texture gradient. Okay, and texture gradient is basically where it's gonna actually combine several monocular cues. So this is when the closer an object is, the clearer the gradient and the detail is, right? You're able to see a little bit more detail. So I'll like kind of zoom in here for you guys to see, like, well, it's not a great picture, but if we take a picture, we'll be able to see it, the gradient and texture closer, then these will look smoother, basically. Okay, so the further it is, it looks smoother. And then we have what's called relative clarity. And this is where it makes clear objects appear closer than blurry or fuzzy objects. So it's kind of like when you use like portrait mode on your phones, that, it looks like everything in the back is in the background instead of, it gives it more depth, basically. So the farther something is from us, the less details it will have. Okay, so that's relative clarity. See, this looks like it's further away, even though the picture is a two-dimensional. Okay. Then we're gonna go to the next one, which is a relative height. And relative height is objects that are higher in our field of vision seem to be further away. So we assume that lower parts of a figure ground is a closer to us. So this a lot of times, like people that are artists, painters, or sketching, they will, if you look here, things that are higher, they seem that they are going to be further away, and over here it'll be closer to us. Okay. Now relative motion is when we are moving, when we are the moving objects. Okay. Objects that are fixed in one place appear to move along with us. All right. So, but the further we are from that fixed point, the faster nearby objects appear to move. So this is like when you're in a car that's moving and you focus on a distant object, that object behind it will appear like it's moving like it's moving along with you, but the objects that are closer to you are going to appear that they're going backwards, okay, when they're really not. Okay, if you're ever looking out a window of a car when you're on a road trip, that's that relative motion. Okay, then we have what's called linear perspective. Okay, and linear perspective is Sorry, yeah, linear perspective, doesn't matter the order, just kind of make sure that you just have at least one drawing or image that you can put into your notes. Linear perspective is where parallel lines appear to meet in the distance, okay? But in actuality, they really are not, okay? So this is like one example of linear perspective. A lot of artists are going to use this. And this is another one. And in actuality, if you look at this, the common like test, these two lines are actually the same distance. Then we have light and shadow, and this is where nearby objects reflect more light to our eyes than distant objects. So we will believe like, so this is where they're gonna play with shadows, and which, like, if I'm looking at this right here, this looks like this is closer, right? Then this one is like metido inside. And that's just because of shadows, but they're technically the same thing. Okay, but the shadows are a little different, just like here. Okay. And then there's what's called motion parallax. And this is when objects closer to us appear to move faster than those further away. So if you're riding on a bus and you fix a gaze on one point, let's say a house, the objects beyond that point are going to move with you. And then the objects, no, yeah, the objects in front of you are going to move backwards. So this is very much like relative movement or motion, okay? Um, and then we have what's called motion perception. How do we see these images in moving, okay? And so basically the human eyes can actually process up to 10 to 12 images per second. Okay, make sure you're writing this down. And then still perceive those images as individual pictures. Now, when you put those images a lot faster is where we see that look like movement, okay, like motion pictures. All right, so we have the first one, which is phi phenomenon, which is a movement of a series of pictures at a rate that suggests emotions, okay? It's kind of like a strobe light, right? So this is a great example of phi phenomenon is motion pictures, right? When motion pictures first came out, it was literally still images of about like 24 frames per second. So they would put these 24 frames, pictures, all together, and then boom, it would look like it's moving, okay? Now like digital film uses about like 29.95 frames per second, or like Blu-ray uses 60 frames. So that's how we're able to basically see movies, but movies are like those still images, they put them together. All right. So, and then our brain perceives those images as movement. So it's pretty cool. Then we have perceptual constancies. And this is when we recognize that an object stays constant or unchanging, even though there's different sensory input that makes them appear that they are changing. All right. And we have what's called color constancy, which is the perception that a color of an object remains the same even if lighting conditions change, right? Like we know that this, even though that this whole entire thing is green, but even though that the lighting has changed, okay? And this is actually giving it some shadows to make it look like it is actually like these squares are darker, but in actuality they are not, okay? Now there's also what's called brightness or slash lightness constancy, which is the perception of whiteness, blackness, or grayness of objects remain constant no matter how much illumination has changed. All right. So this is just with the brightness of things. And then there's size constancy, which is that we perceive objects to have the same constant size, even if there's a distance, right? Like we know that though looking at this image, this picture, even though these people are far away, they're not little, they're gonna still remain the same constant size. But we could use illusions, right? Like we could change our perception, um, because it looks smaller, but our brain is saying like, no, they don't turn miniature, okay? And then there's the shape constancy, which right here, which the object will retains the same shape even if the orientation has changed, right? So even if you're looking here, you know, this door, if it looks like this, even if I change the angle, it will still remain its shape, okay? Now, we have optical illusions, okay? And there's optical illusions are basically, this is where it happens in our eyes and sometimes in our brains, all right? That our brains are like trying to figure out these things. And these are just illusions to mess with the way you perceive information. So you need to know the Muller-Lyer illusions, and these are basically that our lines are exactly the same size, and what they will ask somebody is like, they'll ask them, okay, from this one to this one, which one is longer? And what they found is people that live in Western Hemisphere tend to view this one as longer, right? This one right here as the longer one, when actuality they're actually the same exact size. As you will see here, it's the same size. And what they found is that people that live in homes and buildings that have a lot of rectangles and lines are actually more susceptible to this illusion. Okay, and then we have the Ponzo illusion, and this is where parallel lines on like railroad tracks, like here, as we see here, it leads our brains to believe that the top line, this one right here, is going to be longer than or wider than the lower one because of these lines here, when in actuality, this line and this one are exactly the same size. So that's that. And then we have the moon illusion, which is the last illusion here. And this is where the moon, when it is on the horizon, or it's near like a setting, like in this image you see, you know, build like a fence and trees, the moon is going to actually look bigger, because it's on the horizon and your eyes are comparing it to the buildings around it. But when the moon goes to the middle of the sky and there's nothing around it to compare, the moon is going to look smaller. When in actuality, both of them are exactly the same size. From the one that the horizon to the one that is up here, they're exactly the same size. So pretty cool how that works. And they said like if you want to test this out, you could get like a roll up of piece of paper and then look at just through the hole without removing like all the stimulus from the horizon, and you'll see that they are the exact same size. Pretty cool. All right, that's it for sensation and perception.